Section 2.1 is titled Other Set Operations. So we've actually only encountered one set operation so far. That set operation was complements. And if you remember diagram-wise, we drew a rectangle, we drew a circle, and we shaded sort of outside of the circle, but inside of the rectangle, and that was our operation for complements. We have three more set operations, two that we use significantly in this section. The first one is called set intersection, and then the second one is called set union. A set intersection is much like the intersection of streets. Right? An intersection is where the two streets cross. The intersection of sets is where they have in common, right? The part where they have in common. So in a visual kind of display, we'll draw a rectangle, and we'll draw our two circles. I don't know why they're drawn. It's the way it is. Normally you see them drawn where they're like this, almost like the start of an Olympic rings, okay? So if we have set A here and we have set B here, the set intersection is the symbol, it's an upside down U. Okay. Sometimes people like to think that it looks a little bit like the letter N for intersection, if that helps as a mnemonic device. And then the intersection is the part where they have in common. So that's the football shape in the middle. Notationally, let me shift this up here where I can write beside it a little bit better. This is the set of all x, such that x is an element of A, and x is an element of B. So it's in both sets. So I kind of encourage a visual thought of this being the intersection of streets. Because it works the same way. Union. A union is a set of all objects in one set or the other set or both. So we'll do the same kind of a diagram that we just did. Except that what we get is we get the both, that's the yellow part that's shaded, and we also get the part that's in set A, that's the one set, and set B, that's the other set. One set, the other set, or both. And I should have put a universal set symbol, a U, in both of these. My space is rather limited, so let me slide this over, grab that U before I do it. The symbol for this actually looks like a U for union, so that one's easy to remember. And this is the set of all x, such that x is an element of A, or x is an element of B. So it's in one or the other, but being in both actually gives you that for free. You're in one or the other if you're in both. These are the two we see the most frequently. The next one, relative difference, does come up from time to time. The relative difference is the set of all elements in one set that are not in the other set. So again, from a picture point of view, if I have my same set, I'm going to take out the yellow here. And what we're going to do is we're going to define, it doesn't matter which way we define it, so I'm just going to define A minus B. That's called the relative difference. And this would be the set of all elements that are in set A. So x is in set A. And x is not in set B. So picture-wise, that's this sort of crescent shape over here on the side. It's in set A, but it's not in set B, so it excludes the overlap. Going back to union, I forgot to say this when I encountered it, and given our next problem coming up, it's, I think, valuable to note. Union is not like intersection. Intersection, I said, think of the crossing of the streets. When you think of union, you should think about a marriage ceremony, right? the two become one business or whatever, but that doesn't mean that I don't still have parts of my life, right, that are things that I do, and that my husband doesn't have parts of his life that are things that he does. But we get all of it together. We get to share everything. So it means that if one of you has kids, you all have kids now, right? And if one of you comes in with a whole bunch of money or a whole bunch of debt, you both have a whole bunch of money or a whole bunch of debt. You get it all. So when you think of union, you should very much think of a marriage. And our example that we're going to do for this actually is that. So we have Mary. So consider Mary, single mom to one child, Mark, and Joe, single dad to two children, Jack and Jill. Mary and Joe get married, and together they have two children together, Ann and Andy. If M is Mary's kids and J is Joe's kids, find and describe the following. Okay, blended families happen all the time. Probably half of you are in one of them. Right? This is normal. So we have this first one where it's an intersection. So what does intersection mean visual, like descriptively for this situation? What they share. So these are the ones they have in common. Who would that be in this description? Yep, that would be Ann and Andy. So if I'm writing them out in sort of a curly brace form, I can do it like this. This is Ann and Andy. How about the union? All of them. So this is like the family picture, right? The union is the family picture. So this is all kids. So let's see. We have the Ann and Andy we already had before, so I'll write them first just because I mentioned them a minute ago. Who else do I have? Mark and Jack and Jill. So we get all of the kids. Sorry, my screen was zoomed in too much. I didn't realize I had so much space over there, so now it looks weird. That's better. What is M minus J?
The kids that just married.
Yeah, so these are the only Mary kids. So who are the only Mary kids here?
Mark.
Yep, that's just Mark. All right, they're the kids that Mary has that she doesn't share, at least biologically speaking in our argument, with her husband. Okay? This would just be Mark. Any question about deciphering this from a word picture point of view? There are some properties that our intersections and our unions have that are a little interesting. These are set properties. They have a commutative property, associative property, and then we're going to distribute. They have a distribution property. So this starts to sound like numbers, right? And it is very much related to that idea. So if we have sets, so for all sets A and B, if we have the intersection of two sets, A intersect B, that's the same as the, whoops, I wrote it backwards, the intersection of B and A. Right? If I talk about the intersection of Kickapoo and MacArthur and you talk about the intersection of MacArthur and Kickapoo, we're talking about the exact same place. Makes no difference the order. That's what commutative means. Commutative means I can change the order and it doesn't change the actual components. And it works for intersections and it also works for unions. A union B and B union A. So if we join together Mary's and Joe's kids, or we join together Joe's kids and Mary's kids, we get the same 5 kids. So that's commutative. Associative, as you know, has to do with how we group things together, right? Who you associate with is the idea. So we need 3 sets in order to talk about this. So this is for all sets A, B, and C. Okay, so 3 sets. If we have A intersect B, whoops, there we go, and then we intersect it with set C, that's the same thing as first intersecting B and C, and then intersecting it with A. And I know we haven't intersected 3 sets yet. We will in a moment. But it looks, again, kind of like those overlapping rings, but with 3 rings. And the overlapping region for all 3 is the dead center of 3 rings. And it's true not only for intersections, it's also true for unions. So A union B union C is the same thing as A. Oh, wait, that's how I did it before. So sorry. Union, and then B union C. So again, if I joined the union of 2 sets together and then I add on a third, I could have done it in any other order and it would have been the same grouping of people in the end, or the same grouping of elements at the end. There's one more on my screen, but we'll have to flip to the next page to do it together. 2 more, sorry. One more on this screen. This actually talks about what happens when you try to combine intersections and unions into a statement together, right? So looking at these over here, these over here that I already did, everything is only unions or only intersections, right? They're not unions and intersections within the same statement. Well, that's what happens when we look at this one down here. So we've got the same for all sets A, B, and C that we had before. So for all sets A, B, and C. And what we get is we say if we have A intersect B union C, it's the same thing as intersecting A with B and intersecting A with C and then taking the union. So it kind of feels like that what you're doing is taking this A union and you're distributing it through to each of the sets. That's why it's called the distribution property. All right, so A intersect with B, A intersect with C, and now the union symbol is between those 2 intersections. And all of this idea of intersecting and unioning things actually does some interesting things to cardinality. Now, if you remember, we've talked about cardinality, but it's definitely been a couple of days since we've done that. Cardinality just talks about how many items are in a set, right? So I talked about the people who live in my house right now. The cardinality of the number of people living in my house right now is 7. So that's the number of people living in my house. So when we're talking about the cardinal numbers, there is a formula that we need to keep in mind, and I'm going to justify for you why it works. But it's a formula based on unions. So if I want to know the number of items that's in the union of something, what I actually do is I find the number of items in each individual set and add them together. So number of items in A, number of items in B. And I actually subtract off the number of items in their intersection. I want to show you a picture of why that works because it kind of feels a little bit not intuitive. And then I want to use the same idea to go back to the Mary and Joe's marriage situation to talk about why it works. So let me do a picture first. I've got some space on this screen to be able to show you. If I were doing my 2, actually, oh, I already did, never mind. So those are sets A and B. Here's A, here's B, and here's the union. And I'm going to do this with an argument by shading. So if I'm talking about set A, I'm going to shade in yellow. So set A is in yellow. Okay, so this is the set A. We're going to change colors. We're going to shade set B in orange. So set B in orange would be this set. And hopefully you noticed that I double shaded something, right? So everything that's in that overlapping piece in the middle, namely the intersection, got shaded twice. So the reason you see us subtracting it out is because we're removing the double counts. So if we were to go back and we were to talk about Mary and Joe, if you were to count the number of Mary's kids, I'm thinking biology again here, how many kids did Mary biologically have in our description? Whoops, that was it. She had 3, right? She had Mark originally, and then she had Ann and Andy. So Mary had 3. If we had the number of people in Joe's, right, number of children that Joe had, how many did he have? 4. They do not have 7 kids, right? The problem is, of course, is that we counted Ann and Andy twice. So what we really have to do is we have to figure out how many they have in common, or at least if we're trying to make this comparison to show why it's working. The number of kids that Mary and Joe had in common, which was 2, would actually get subtracted. So I have my 3 plus 4 minus my 2, and there are the 5 kids that I know that I have. There's a double take going on. Now, if the sets don't have anything in common, right, like if Mary and Joe got married and they did not have any additional kids, this would be irrelevant. They would be completely disconnected circles. There wouldn't be an overlap. So that's a possibility. But if there is any overlap, we have to take that into consideration. There's one more piece of information before we get to some cool pictures. And I think we might be able to do 2 more examples. Well, like the next one, Cartesian product, and then example 2a. So Cartesian product is the set of all ordered pairs such that the first component comes from the first set and the second component comes from the second set. This kind of feels like what we did when we were looking at one-to-one correspondences. Right, so we have this collection of guys that walk into the room. We have a collection of girls that walk into the room. We make this one-to-one correspondence of people. But what we're going to do in this problem is we're going to actually write down all the correspondences instead of how many correspondences there are, though we'll talk about that. So I'm going to do an example that is easy to identify the different pieces. We're going to do the set A that has the letters X, Y, Z. And we're going to do the set B that has numbers, just so that we're differentiating easily the numbers 1 and 2. So if we are finding the Cartesian product, it actually looks like multiplication and big ol' X between them. And it's not a dot. It really looks like the X for multiplication. And what we're doing is we're grouping things together. For example, I'm going to start with the letter X. And I'm going to pair X with the number 1, and I'm going to write it like an ordered pair. I'm going to pair X with the number 2. And those are all the different ways that X can be paired, and I'm done. Now notice there isn't a one-to-one correspondence here, but I could still do pairings and talk about how many pairings there are. But maybe I don't start with X, maybe I start with Y. Well, I could do Y with 1 or Y with 2. Or I can do Z with 1 and Z with 2. So the Cartesian product is simply a set of pairs of elements where one element comes from one set and the other element comes from the other set. Notice there is no ordered pair that says XY because they both come from set A. Right? I need one thing from set A, one thing from set B. It is very interesting to notice that there's an interesting correlation here between the number of items. So how many items are in set A? 3. How many items are in set B? 2. And how many items are in the Cartesian product? 6. So what's the relationship that's happening between the 3 and the 2 to get 6? Yeah, it's actually a multiplication situation. So if I take the number of items in set B times the number of items in set B, I will have the number of items in the Cartesian product. And that works all the time. So you want to be a little bit careful what the question asked. Did it ask you for the Cartesian product, in which case you're writing this out up here? Or did it simply ask you how many items are in the Cartesian product? It asked you for n of AB. Right? If it's only asking you for n of A cross B, like this one, you don't have to write them all out to find that. You could simply count the individual pieces that you were looking at beforehand. Do you see the two questions I'm talking about? One question says, maybe find A cross B. The other one says find number of A cross B. And this one down here is much quicker to find. You don't have to write everything out to do it. All right, I want to show you some cool stuff about Venn diagrams. I maybe have time for the 2 on this page, actually. Okay, so we're starting out with this example where we have 2 sets. So our picture is going to look like the ones that I've been drawing with a rectangle and 2 circles inside. Okay, so yours will look better than mine because I have to keep shifting things around to make it work. Looks something like that if I shift them right. I want to label the letters the way that they're given to me. So this is set A, this is set B, and we'll always have a universal set U. Now, let me just make a comment on this for this example, for instance. You might be able to, because there's only two sets and because there's not a lot going on with those two sets, reason out which area of the diagram that is referencing. What part is A complement union B complement? So you might be able to reason that out pretty directly on this one. But if you take a look at the next one, it becomes more difficult because there are three sets. If you take a look at the third one, not only are there three sets, but some of them have complements and some of them don't. So the complexity gets really crazy really quick. So I'm going to show you a structure on something that maybe isn't necessary to use it on, so that when it becomes necessary, you have that in your tool belt. Okay? So here's what we're going to do. We are going to identify the areas or the regions of our diagram. And we're going to do that by labeling them with numbers. 1, 2, 3, and we've got a 4 on the outside. There's nothing special about the numbers 1, 2, 3, 4. You could literally use any numbers that you'd like. These are just nice things to use. You could use letters. If you wanted to, go with the things they're doing right now, you can go alpha, beta, gamma, delta. I don't care, right? I mean, they keep, COVID stuff. It's all gamma. It's all letters of the Greek alphabet. That's what they're using, right? It's interesting. So it doesn't matter if we use numbers, letters, whatever. I think numbers are easier, so that's what I usually use. And I think there's some examples in your book where they use some letters, like A, B, C, D or something. But since I'm using capital A, B, and U, I'm going to use numbers. So here's what we're going to do. We're going to take each of the individual pieces, and we're going to write them down. If they have a bar on top, we're going to write them with a bar on top. If they don't, we're not. So we have A bar, right, A complement, and B complement. Those are our sets. So for A complement, what we're going to do is we're going to look at all the numbers I wrote down, 1, 2, 3, 4, and we're going to ask ourselves which of those numbers are in the complement of A. And which ones are? 3 and 4. So A has 1 and 2. A complement has 3 and 4. So remember, complements means they're not in A. So thinking about it like that, we're going to do B complement. Not in B. 1 and 4. It's okay. We're all practicing, so it's okay if you're making mistakes. So everybody see where the 3 and the 4 and the 1 and the 4 came from. If you don't, say something. Jordan, are you looking confused for me? Good? Okay. It's really important we get the numbers written down right, otherwise we're not going to be able to proceed through the problem correctly because we've got a mistake already. So we're going to write down the individual listing of numbers that satisfies the descriptor. And then on this one, there's only one other thing to do. It's to do, I didn't mean to draw that. It's to do the union. So we're going to take A complement, union, B complement. So remember, union means you get everything. So I have to get all those numbers that are written up there beside the A complement and the B complement, but I don't need to write things twice, right? I recognize ones in both lists, but once I write it down once, that's enough. I don't need to write it down twice. So this is 1, 3, and 4. What would it be if it said A complement intersect B complement?
4.
It would just say 4. Yeah, I don't know why I said 1 twice. 4 twice is what I meant. Yeah, it would just say 4, because 4 is the only thing they have in common, right? And that's what intersection means, is in common. But this one is union, so we get 1, 3, and 4.
I don't understand. If it's not in A, why is 1 on there? And then if it's not in B, why is 3? You know?
Okay, so do you mean in my final result? Oh, good grief.
Yeah, in your union of A complement and B complement.
Okay. The same reason that if I said Mary's kids union with Joe's kids, Mary's son Mark gets included even though he's not Joe's kid. Right? The same thing's happening. So we're including everything that's not in A and everything that's not in B.
Okay.
So we have to include all those pieces. So the things that are not in A are 3 and 4. So they get included in the union.
Got it.
The things that are not in B, 1 and 4, they get included in the union.
Okay.
And then when I compare them all together, There's 3 pieces right now, 1, 3, and 4, that are not in the union. Okay? Thinking about this, we didn't answer the question yet, or we didn't actually finish it. What did it actually ask me to do in the directions? Shade. This says to shade. So feel free to use a highlighter, a crayon, a colored pencil, or you can shade with your regular pencil. It doesn't matter. But we're going to shade the areas of the graph represented by these 3 numbers. So I'm going to shade the number 1. I'm going to shade the number 3. And I'm going to shade in the number 4. So the only thing that should be left unshaded on this problem is the number 2. Okay, let's try one with 3 numbers. There's no complements, so that will make things a little easier. You're going to draw the same rectangle, but you need 3 circles inside now. And they look something like that. And I'm going to label them across the top, A, B, and the one at the bottom, C. Okay, so diagram okay so far. Now hopefully, as you look at this, you say to yourself, there's more than 4 regions. Yeah, there's more than 4 places that I could put numbers, so I will have more than 4 numbers. I'm going to label straight across the circles, so 1, 2, 3, and then through the middle, 4, 5, 6. The bottom part for C will be 7, and then the outer part for our universal set will be 8. There are 8 different regions. And we will never have more than 3 circles. Thank goodness, right? Yeah, 3 circles. So our process is going to be much like we did on the last problem. We don't have any complements, but we have to remember things like order of operations. I have parentheses, right? We always do things inside the parentheses before we move outside the parentheses. So as I'm working with this problem, I'm starting with the inside of this parentheses. And in particular, I have 2 sets, A and B. So I'm going to write them down, A, B. What are the numbers inside circle A? 1, 2, 4, 5, in whatever order you like. But yeah, 1, 2, 4, and 5. What are the numbers inside circle B? 2, 3, 5, and 6. Okay, is everybody good with that? Okay, we've done the individual pieces then inside the parentheses. Now we're ready to join them, right, with the intersection. What does intersection mean? Things they have in common. So what numbers do you see in common on both lists? 2 and 5. So this is 2 and 5. So if I were only doing the circle, I mean the parts that represented the part that's in parentheses, 2 and 5 would be the ones that I would have. I have another set to consider though. I'm supposed to use set C as well. So what numbers are in set C? 4, 5, 6, and 7. So I've taken care of the C part. And then the last thing is to take the union of those last 2 sets, namely the union of the A intersect B that I found and the union of C, right, with the union of C. What does union mean? All of them. So every number that's listed here is going to get rewritten in my union. So if I go in order, I've got 2, 4, 5, 6, and 7. And what would my last step be? Right, to shade those regions. Here's 2, 4, 5, 6, and 7. Any questions on that one? Okay, we will start back with the next page next time and finish up section 2, 3 then.